standardize, and that should make you think, oh, this is a titration example, and you want to write out the reaction. So let's do that. Oxalic acid, H2C2O4, that's oxalic acid. Okay. Plus sodium hydroxide, NaOH, goes to, now this is neutralization or double replacement, sodium oxalate, need 2 sodiums, because oxalate is 2 minus, plus water. And then I need balancing. So I'll put a 2 in front of the water and the sodium hydroxide. Here's my balanced reaction. Now underneath, I'm going to write the information I know. So there's 0.424 grams of oxalic acid. There's 32.15 milliliters of the sodium hydroxide, and I want to know the molarity. Okay, so I'm going to start with what I know. Convert to moles, molar ratio to get to this compound, and then convert to what's asked for in this case, molarity, which is moles per liter. Alright, so let's try that. We've got 0.424 grams of the oxalic acid. I want to convert that to moles, that's my first step. There's 90.04 grams per mole. And so now this is moles of oxalic acid. I'm going to use a molar ratio to go to what I want, which is sodium hydroxide. So there's 2 moles of sodium hydroxide for every 1 mole of oxalic acid. So now I'm at moles of sodium hydroxide. Let's see what that number is. That's 0.00942. Again, moles of sodium hydroxide. Now, what I'm going to do is use this to convert to molarity. Okay, so I have moles, I'm going to go to molarity, I need moles per liter. Let's go down to the next line. Well, that would be 0.00942 moles on top in the numerator, divided by the volume, which is 32.15 milliliters. However, the volume is in milliliters and it should be in liters. So it's 1,000 milliliters per liter. And this turns out to be 0.293 molar sodium hydroxide. And that's a pretty typical titration example. Follow your 3 steps. Convert to moles, go to the molar ratio of what you want, then convert to the units you asked for. Okay, there's one more example. And the second one was from chapter 6. Right here, we have a manometer, and here we want to find the pressure of the gas in the diagram. Okay, I gave you a height difference and a couple pieces of information to help us solve this. Let's try it. Okay, in this example, first of all, if I wrote P gas and P bar, pressure of the gas, pressure of the atmosphere, which one's larger numerically? The pressure of the atmosphere, P bar, is greater. How do we know that? Because it's pushing, you see the arrow here that represents the pushing of the pressure from the atmosphere. It's pushing harder than the pressure of the gas. So thus it's pushing the liquid level lower. This silver part here is the liquid level. So it's pushing harder, so thus it must be greater. To write this in terms of an equation, I would say, well, P gas plus some change in pressure equals P bar. Because it's smaller, I'm adding some change in pressure due to the change in the liquid level height. Okay? That. So then, I want to solve, let's see, for P gas. So really P gas, because that's what I want, find the pressure of the gas, is P bar minus this change in pressure from the liquid level height. Okay, and let's take one more step. P bar. This change in pressure is the formula we saw a week ago. Density times gravity times change in height of the liquid level. So pressure, change in pressure is density, gravity. Okay, now we've just got to find all this stuff and plug it into this formula. So this is the formula I'm going to use right there. I just need to find all the information. So let me work on all that info right now. Let's see. The pressure of the atmosphere, or P bar, is, it depends what units you use, like 1 atmosphere, or you could say 760 millimeters of mercury. All this will be in a conversion chart on your second exam. But we want, this is the kind of problem I'd always recommend you use SI units. It'll be easier. So I recommend SI units only for this equation. And SI units is 101,325 newtons per meter squared, which is a Pascal. So that's your atmospheric unit for pascals. That would be P bar. And then let's get the other ones. Gravity, that's just the gravity on Earth, 9.81 meters per second squared. That'd also be something that was given. The density, let's do the change in height first. The change in height is 10.19 centimeters, but really I want to put everything in SI units to be consistent. So in meters, that would be 0.1019 meters. Now, let's see what's left. I need density. So let's work on density now. That needs to be in SI units. I have 13.6 grams per centimeter cubed. So let's change this to SI units. I need to change grams to kilograms. Kilograms is SI unit. And then I need to change centimeters. There's 100 centimeters per meter. But notice that the centimeter is cubed because it's a volume. So this centimeter has to be cubed. I have to cube the whole quantity. That means I'm really going to multiply by 100 cubed or 1 million at this point. This is going to turn out to be 13,600 kilograms per meter cubed. All right, I have everything in SI units. I'm just going to plug in right now. So let's plug into that formula I have circled here in red, right there, which is P gas equals P bar, 101,325 newtons per meter squared, minus density, 13,600 kilograms per meter square, meters cubed. Gravity. Gravity is 9.81 meters per second squared. And then change in height. I found that 1.1019 meters. So everything's in SI units. I just need to solve. When I did this, I got 87,730 Newton per meter squared, which is a Pascal. And then really, it looks like we'd only have 3 sig figs here, so probably the answer is really like 87,700. Okay, so that's a typical manometer problem. Make sure that you convert to SI units, and otherwise you plug and chug from that point. We're good with that one. First, I'll leave the bottom part in case you're still copying. And we'll take a look at our schedule. What we got. Okay. Okay. Cool. Alright. Normal check for the next day. Okay. With that last example, we're totally done with chapter 5. We're in chapter 6, and last time we did the first section of chapter 6. So let's keep on going. By the way, office hours is normal on Wednesdays. Okay, let's see. I want to show you this. This is on page 42 of the reader. I already showed you this before, but just to see where we're going. All we did so far was the gas properties box. Okay? Just a visual map of this chapter. We've done the gas properties box. Now we're going to go to this box right here, this monster section here on the left-hand side, and talk about the kinetic theory of gases. And that involves all these pieces here. Okay, so we're going to start out with the 5 assumptions, and then we're going to move on kind of around this box here. Okay, so that's where we're going. Okay, and as I mentioned last time, we're doing this chapter out of order. So after finishing section 1, we're going straight to section 7. We're going to come back to 2 through 6 a little later. Kinetic theory of gases. And this is on page 44 of the reader and page 218 of the textbook. Okay, there are some assumptions. I'll make some bullets here, 5 bullet points or assumptions about that we use to derive a theory of gases. That theory of gases we call the kinetic theory of gases. Okay, gases are tiny molecules. They're so tall, so tiny, we consider their volume 0. So we assume that gases take up no volume. Okay, they're infinitesimally small. Okay, gases travel in straight lines and randomly though. What does that mean? They're bouncing off each other, off the walls, going random directions. Not predictable, but when they're between bouncing off something and another thing, they're going in straight lines. The third assumption, there's no attraction. So, unlike the dorms or college, when gas molecules pass by each other, there's no movement, there's no interaction whatsoever. They don't see each other, they just pass by. Okay, no attraction between gas molecules. Number 4, bullet number 4, elastic. So they undergo elastic collisions. What does that mean? When they bounce off each other, there's no loss of energy. So they bounce and they still retain, either energy is transferred, but there's no loss of energy. Okay, so only transfer of energy, if anything. And then number 5, the kinetic energy, which we symbolize this in the textbook, so I just follow a textbook symbol, E sub K. The kinetic energy, what's this wiggly symbol mean? Is proportional to, it's not alpha, is proportional to, alpha is this. See the difference? Is proportional to temperature. So kinetic energy is proportional to temperature. Let me take a moment to explain this one. As temperature increases, the kinetic energy increases. Okay? So if you consider the gas molecules in this room, there's nitrogen, there's oxygen, what are the gases would be in this room? The third most common would be argon. At this temperature, all those gases have the same average kinetic energy. Okay? So it doesn't matter what the gas is. At the same temperature, all the different gases have the same average kinetic energy. Okay? And on average, those are all equal. Alright, those are our 5 assumptions. Then what you'll see, there's a couple mathematical concepts to know, 3 of them that I outline in the reader, in order to kind of go on discussing this loose derivation of the kinetic theory. Okay, number 1. So this will be 3 governing equations, really, to help us kind of make some progress and understand this kinetic theory of gases, or this theory of gases. Okay, There's a formula for kinetic energy, and that's kinetic energy. It's equal to, you might have seen this in physics before, 1/2 mu squared. U is velocity. Okay? Let's think about this. Okay, at the same temperature, remember from before, kinetic energy is on average is the same. Okay? But in our room, say we have nitrogen N2, we have O2, we have argon. According to this, if the kinetic energy is the same, the heavier a molecule gets, the slower it goes. You see how mass goes up, U has to go down, keeping kinetic energy the same. If mass goes down, kinetic energy must go up. So that's a main concept that you want to remember. Faster things will be lighter, and then slower things will be heavier. And that's according to this formula. As mass goes up, U must go down, and vice versa. Okay, number 2. Second governing equation has to do with something we call collision frequency. Okay, remember, here's our proportional to. And we're just talking about collisions here. So in collisions, if something's going faster, do you expect more collisions or less? More. Hopefully that makes logical sense. If you raise the speed limit on I-80, then, or those of you from LA, the 80, then the collision frequency will proportionally go up. Okay. Let's think about volume. If there's more space, are there more or less collisions? You would expect less collisions, so I'm going to put volume down here. As volume goes up, collisions should go down. Okay, the roads are bigger, there's less collisions. Okay, and then let's make a little side note here. You remember Avogadro's number, and in this chapter, moles is represented by lowercase n. So Avogadro's number times lowercase n, moles. What's all that left? What's all that's left if I multiply moles by Avogadro's number? Atoms or molecules. So this n, capital N, we're just saying is the number of molecules. Now, Avogadro's number is molecules per mole. But you multiply by moles, you just have molecules. Okay. Collision frequency. As you increase the number of molecules, what happens to collision frequency? Up or down? Has to go up. If there's more cars on the road, more molecules out there, there's more collisions. Okay. This is our governing equation for collision frequency. All right, number 3. Okay. You've heard of momentum. Probably. It's also, you might not know, it's also called impulse. For some reason, the book really likes the word impulse, so I'm just going to stick with it. And it's symbolized by the capital letter I in the book, which we're just going to go with the flow. So impulse or momentum is proportional to, if you have, the higher the mass, the more momentum something will have. So mass is going to be proportional to momentum. The more massive something is, the more momentum it's going to carry. And also, the higher velocity something has, the more momentum that item will carry. So momentum, or impulse, is going to be proportional to mass times velocity, which you might have seen in a different form in physics or something. Now, we're going to use these 3 equations, and I'll show you how. At the time being, let's focus on number 2 and 3. So number 2 and 3. Pressure is actually proportional to momentum. Hopefully that makes sense. So you imagine a container, the wall, like the wall of this room. The more momentum something has hitting the wall of the room, the more pressure it's going to have. So pressure is proportional to momentum. And it's going to be proportional to collision frequency. I'll just abbreviate collision frequency like that. So the more frequency of collision something will have hitting a wall, the higher the pressure will be. So that's how we think about pressure. And let's just use these two formulas right here to kind of rewrite this expression for pressure. Mu times UN over V. Or if I rearrange a little bit, N over V mu squared. Okay, there's a little expression for pressure. I'm going to rewrite this one more time. Pressure is proportional to N over V mu squared. Now I'm going to change the U a little bit. The U is, remember, that's velocity. But really, when we have a lot of gas molecules, the gases have different energies. We don't know exactly what the particular velocity is, but we can measure an average velocity. So, and the way we denote average is to put a bar above the letter. So, U squared bar means the average of U squared. And so that would be called the U squared bar is the mean square velocity. And that is the sum of the U squareds over the total number. Total number of molecules, etc., whatever you have. So it's the average of the U squareds. And then again, the reason we're using this is because every molecule might not have the exact same velocity, but they'll have on average the same velocity. Alright, now, some of you I know wish that you were in honors chemistry, so you could do more derivations and use more derivatives and partial differential equations in class. Unfortunately, we're not. If you need more of that, you can drop this class and take honors. But what we do when we get too crazy with derivations, we do the following. Dot, dot, dot. Okay, derivation stuff happens. Okay? We're going to skip the derivations in this class. If you want to see more detail, again, you can look in the reader on 44 and following. You can look in the textbook, 219 and following. They don't do all the derivation in fact, but they do for the most part. You can see what's going on if you want more detail. Unfortunately, sorry, we're not going to do that. But I will put 3 dots here so that you can see something happen, whatever that was. Okay. Pressure is going to be equal to 2/3 N over V. The N over V is still there. And EK jumped in. EK is kinetic energy. Where did that jump in? Well, notice it's 1/2 mu squared. That's where the EK came from a 1/2, so that's where that 2 came from. The 3 is going to come from 3 dimensions in space. Anyways, we skipped how that happened. It just happens magically, whatever. Alright, now, I'm going to rewrite this again. 2/3 over V. N, remember, is N. Remember I made that little definition earlier for capital N times EK. I'm going to rewrite this just one more time a little bit. 2/3 little n over V. And I'm going to move the Avogadro's number over here with EK. Why do we do that? Commonly people like to make a little definition with these two right here. That would be kinetic energy per mole. Do you see that? Because Avogadro's number is per mole. So that would have units of kinetic energy per mole. And what we call this is the average kinetic energy per mole of gas particles. This is the average kinetic energy per mole of gas particles. And we write it. It just comes convenient to write it, rewrite it, and not write all these variables. It's EK squiggly. What is EK squiggly again? It's the average kinetic energy for a mole of gas particles. EK squiggly. Alright? So, rewrite that again. That is 2/3 little n over capital V, moles over volume, times EK squiggly. Okay? Now, let's just move a couple things around. I'm going to move the V over here. I'm going to move the N over here and say this is 2/3 EK squiggly. So I just moved a couple variables over. Now remember, I'll put this in a different color. Remember, according to those 5 assumptions, EK squiggly or EK, doesn't matter, it's proportional to what? That's your 5th assumption. So I'm going to toss this in here. PV over N must be proportional to temperature. Let me rewrite this a little bit. PV is proportional to NT. And now let me toss in a proportionality constant. PV, let's call that proportionality constant randomly the capital letter R, and let's randomly put it between N and T. What is this? This is the ideal gas law. You've seen it before in high school chemistry. It actually can be derived. Okay? You can come experimentally, but you can also derive this ideal gas law. This R, which is called the ideal gas law constant, that has to come from experiments. But the cool thing about this kinetic theory of gases, we're able to derive a law to describe gases. We call that the ideal gas law. We're going to use that more later, but I will at least right now tell you about R. R is the ideal gas law constant. It's just a constant. And we're, again, going to do calculations with this later. So you'll see us use it later. But it's 0.08206 liters atmospheres per mole Kelvin. It can be in a number of different units. That is the most convenient unit for this, for doing these types of calculations. There are other R's, of which you'll see one momentarily. Now what we're going to do, we're also going to mess around with this EK squiggly here. It did not drop away from our memory banks. So, let's go back to the 2/3 EK squiggly was proportional to temperature. Okay? 2/3 EK squiggly is proportional to temperature. Let's move this around a little bit. EK squiggly is proportional to 3/2 T. Okay, let's make this an equal sign and put in a proportionality constant. Let's call that capital R, and again, for some reason, we'll put it in the middle of 3/2 and T, just like we put in the middle of N and T earlier. And now, this is another formula for kinetic energy. That is still R. It's still the ideal gas law constant, but it is more convenient for this formula to use different units. So same R, just different units, 8.3145 joules per mole Kelvin. So we still have per mole Kelvin, but liters atmospheres is converted to joules. Again, still the ideal gas law constant, just in different units. And now, what do we get out of this? There's a couple things to know. You can derive a formula for the ideal gas, describing the gases, and we call that the ideal gas law, and that's this. Again, we're going to use it later. We're not going to use it right now. We'll use it probably in the next class. And then we have a formula for kinetic energy in addition to the other one you saw earlier, which is 1/2 mu squared. Okay, so you saw this one earlier in our governing equations. You're going to derive a second formula for kinetic energy. And as soon as we do a little more work, I'll show you how to use these formulas mathematically. What else can we say about this? So, kinetic energy, again, let me say a little bit more about it. It's the energy of motion. It's the energy of translation or movement. And notice what happens at 0 Kelvin, there's no kinetic energy. That means when you go as cold as you can possibly go, which is 0 Kelvin, absolute zero, things don't move anymore. Okay, at least translationally, things are not moving around. As you increase the temperature, things move. So the higher the temperature, the higher the kinetic energy, and ultimately the higher the velocity.